let me move on to this week's and first speaker for this virtual version of the Stochastics and Statistics Seminar. And it's my great pleasure to welcome Jonathan Niles-Weed from NYU. So as many of you know, Jonathan completed his PhD at MIT under my supervision. So we know each other quite well. And it was a real pleasure and to have him as a student. And I kind of miss him, so I'm happy that he's back. So Jonathan completed his PhD as part of the interdisciplinary doctoral program and received a PhD in mathematics and statistics. So it's not surprising that he chose a job which is halfway between mathematics and statistics. He's currently half with the math department at the Courant Institute at NYU and the Center for Data Science. In terms of award, John received a couple of awards during his PhD, including an NSF award, NSF fellowship, and a De Carman fellowship. His work spans learning under algebraic structure, optimal transport, and he's currently working on problems related to discrepancy. And throughout all of this work, he's been working on high-dimensional phenomena, both in statistics and probability. And so today he's going to talk about something which seems to be more in this last part about matrix concentration for products. So John, please take it away.
Wow, thank you so much, Philippe, for the extremely kind introduction, and thank you all for being here virtually. I would prefer to return to MIT to get to hang out with all of you, but in lieu of that, we can socially distance and I can be at MIT from afar. So today, as Philippe said, I'm going to be talking about some new work on matrix concentration for products of random matrices. This is joint work with some wonderful co-authors, De Huang, who's a PhD student at Caltech, as well as Joel Trop and Rachel Ward. So the starting point for our investigations is a question that I think I don't need to convince you is an important and interesting one, which is just a question to which a great deal of effort has been applied over the course of the history of probability theory, which is when I have some function reasonably nice in some sense that I would like to make precise of independent random variables, when is it the case that this function concentrates well around its expectation? And in particular, how can we make quantitative this concentration effect, which ensures that we're actually close to the expectation of this function? And so this type of question has driven the growth of a tremendous number of new ideas in probability theory. It's the central question in the concentration of measure phenomenon. And by now we have very sophisticated ways of understanding the answer to this question for a number of functions of interest. So, you pull open Ledoux's book on the concentration of measure phenomenon, and he says that, we now have a sort of high level view that when the function is nice or smooth enough, that these sort of concentration properties hold essentially automatically. And, there's a great theory surrounding them that allows us to prove very sophisticated things for very seemingly complicated functions. So a superficially similar question is the following variant. I can ask exactly the same thing, but I can ask what happens when instead of scalar random variables, I have matrix random variables instead. And these two questions look extremely similar, but I would argue that we lack a great deal of sophisticated technology in the second case that we do have in the first case. And it turns out, as we'll see a little bit later, the key problem here is non-commutativity, right? Like we're working with random variables that don't have commutative structure necessarily. And as a result, many of the powerful and simple ideas that exist for scalar valued random variables are much more complicated to instantiate when it comes to matrices. So to give an example that I'm sure many of you are familiar with, let's go back to the first concentration inequality you might see for scalar random variables, which is Bernstein's inequality, which reads like this. I have a bunch of independent random variables, say they're all mean zero and bounded almost surely. If I apply this trick of using Laplace's method, which bounds the moment generating function, then I can get a nice tail bound for the average of these random variables, right? I see that the average deviates from the expected value, which is zero, by some amount t, by a probability that decreases exponentially in t. And we see in the tail bounds that you get this subquadratic, this sub-Gaussian growth in the exponent, and you also get something that adapts to the fact that the variance of these xi's might be small. And so this is Bernstein's inequality that I think is an early one that you would learn in this concentration of measure, in these questions on concentration of measure. So as I said, the proof of this is very simple, right? The one trick is to apply Laplace's method. So put everything on the exponential scale, then use the fact that for a sum of independent random variables, the moment generating function just turns into the product of the individual moment generating functions. And then the bound that I have on the individual xi's allows me to bound this quantity easily for each of the random variables. Then I can apply Markov's inequality and I'm done. So this is an example that's known to everyone. And I think a very reasonable question to ask is whether the exact same statement is true when it comes to random matrices. So if I have a bunch of independent random matrices now, d by d, still with expectation 0, whose spectral norm is bounded by 1. I'll always use these double bars to represent the spectral norm of the matrix. Is it again the case that the average of these random matrices deviates from its expectation with exponentially small probability? And before I think this is a mathematically interesting question on its own, but of course, one reason that people have asked these questions is it turns out to be super useful to have bounds on this sort of thing in a number of modern statistics and machine learning style problems, right? The original example of this maybe is covariance estimation. If I have IID samples from a random variable and I want to estimate its covariance matrix, then naturally I'll get something that looks like this showing up. But it also turns out to be useful throughout statistics, like I said, like many ideas in random graphs, sparsification, algorithmic ideas involving randomized linear algebra, dimensionality reduction, all of them need bounds on quantities of this form. And so one reason that we might be worried about this is because if we try to just ape the proof that we had of Bernstein's inequality, then we fail at the very first step somehow, right? I can still form the matrix exponential of all of this sum of random matrices, but unless the matrices commute almost surely, I have no way of turning this into a product of the expected matrix exponentials of the individual matrices, which was what I needed to do to be able to apply my assumptions on the xi's. So it's a very similar looking inequality, but I can't apply the proof that I know. And so the insight here, or the idea here, and this was a series of ideas developed over the last 20 years or so since the work of Niles-Weed and Winter in 2002, is that I can get exactly the same inequality, but in place of the trivial equality involving matrix generating functions that I used for scalar random variables, I need something quite a bit more sophisticated. So, we've replaced the equality we had for regular scalar random variables by this significantly deeper inequality, which then we can use to complete the proof as we would originally want to. And the thing I want to point out here is that I get a tail bound that looks exactly the same, apart from this factor of D out front, which is the price to pay for the fact that we're working with D by D matrices. I see a tail bound of exactly the same form, sub-Gaussian decay, plus involving something that looks like the variance of these random matrices. And here, what do I mean by variance? Well, in the scalar case, I was just taking the sum of the expected squares of the random variables. Here, because they're matrices, not necessarily symmetric, I have two different ways of taking their squares, and then I just take whichever one of these is bigger. So this, as I said, inaugurated by Niles-Weed and Winter in 2002, and then this particular formulation discovered independently by Oliveira and Trapp a few years after the Niles-Weed and Winter bound, shows that you can get stuff that looks exactly like the scalar case, but what you need is one idea, right? Like you need some non-trivial fact about matrices that replaces whatever you were using in the scalar case. And I think this is the pattern of many ideas involving random matrices, that you start with what you understand from the scalar case, but then you need to reach deeper into your toolbox to get something non-trivial that you can use to deal with the non-commutative nature of these operators. So, okay, that is the simplest possible case. That's the so-called matrix Bernstein inequality. And our question today is just, let's go for the next most complicated function, right? We said now a sum of random matrices that are bounded is something that we can handle via these matrix Bernstein ideas from about 10 years ago. And what we want to understand is what happens when you have a product of random matrices instead. So again, just as was the case with the sums of random matrices, I think this is a natural mathematical question, but actually I would argue also that it has practical importance in some recent questions that are being asked in statistics and machine learning. And the key insight is that the reason you might care about products of random matrices is that these are really compositions of random operators, right? If I apply a product of random matrices, I'm just applying random operators one after each other. And this starts to sound like a lot of things that happen in machine learning these days. I mean, certainly I can go back to control theory and think about linear dynamical systems, which have this flavor, right? Some random operators being applied to my system at each step. But when I'm doing stochastic optimization on a quadratic, say, or I'm interested in the Jacobian of a deep neural network with randomly initialized layers, I get something that looks like a composition of these random operators. So if I want to understand the extent to which this object concentrates or behaves well, I need to understand the question about how well products of random matrices behave. And just as was the case when we were looking for the Bernstein inequality in the case of the sum, the quantitative question will be, can we take what we understand about the scalar concentration inequalities for products and give a bound that's quantitatively similar to that bound? Right? Can we show that we don't really lose anything when we pass to matrices, or can we quantify precisely how much we do lose in going to the matrix rather than the scalar case? So that's going to be the question today. Can we understand concentration for products of random matrices in a form that's just as general and just as widely applicable as we can for sums of random matrices? So this is not a new question, but the perspectives that have been applied to it in the past, I would say, are a little bit different from the perspective that we apply in this work. So there is some really classical work on what happens when you take products of random matrices. And the earliest work is due to Bellman, who considered a sort of interesting setting, which is, let's pretend that the matrices that you're multiplying have entries which are positive almost surely and bounded. So bounded away from zero and bounded away from infinity. I have IID copies of such matrices. And then what this asks, if I take the product of these random matrices and then entry-wise look at the logarithm of each entry and renormalize, what is the behavior of that random object? So it turns out that work of Bellman and then followed up by Furstenberg and Kasten show that there's a law of large numbers, and also when properly renormalized, a CLT for this entry-wise object for positive random matrices, positive in the entry-wise sense. So that's the earliest work on this thing. Again, they're not interested in non-asymptotic concentration bounds there. They're just interested in what's the asymptotic behavior of these objects. Slightly closer to our setting, but still in the asymptotic regime where you just care about limiting distributions, Berger in the 80s worked on the question, not where you have matrices who are positive almost surely in the sense of entry-wise, but matrices instead which are perturbations of the identity matrix. So I have matrices of the form identity plus something small. I have a product of a bunch of those. And again, I want to ask, when I multiply these all together and suitably renormalize, what does the resulting object look like? And Berger again proved law of large numbers and central limit theorems for random matrix products of this type. So that's the classical picture. Some work in the 50s and 60s, some later work in the 80s, but all done more or less from this perspective. Another sort of take on this problem comes from the world of free probability, which is, the brainchild of Voiculescu. I'm sorry to any Romanian speakers in the audience. Over the past, 35 years, has developed this very sophisticated set of techniques to understand what happens in this non-commutative probability case. And there, I would say that the approach is again somewhat different from the perspective we're taking, because really what kicks in free probability is the asymptotics as the size of the matrices gets very large. So there's this notion of asymptotic freeness in free probability that is really asking what happens when I have a product of a small number of matrices, but where the dimensions are going to infinity. And in that case, we can say very precisely what happens to the spectrum of these products, because you get this freeness that turns into a type of convolution of the matrices in question. So there we're taking asymptotics, but in a different sense as the size of the matrices goes to infinity. The other case that's well studied and for which very exact results exist are, of course, if I impose a great deal of structure, right? So if I require that my random matrices come from some invariant ensemble, say that they're all Wigner matrices or Wishart matrices or something like that, then I can actually, roll up my sleeves and write down what the say spectral density of the resulting matrix is when I take products of these guys. But this is really relying very heavily on the Gaussianity or the general invariance of the matrices in question. So if we're looking for, I would say, user-friendly and widely applicable bounds, these give some insight into what happens in a very particular case, but we want stuff that works far outside the Gaussian regime, because in any of the examples that I talked about where you're composing random operators, you can't just a priori assert that anything Gaussian or invariant is going on. So these several lines of work are all thinking about this problem, but sort of from different perspectives. And I would say that the starting point for our work is much more recent. It's a paper by Amelia Henriksen and Rachel Ward. Rachel's one of my co-authors from 2019, where they, I would say, wrote down the first non-asymptotic concentration bounds for this problem that really have the flavor of what we're looking for. So let me just show you what this theorem of Henriksen and Ward is. They say, okay, you have a bunch of IID matrices, and they're bounded almost surely. So far, this looks exactly like the Bernstein case. And you form this random product. So the random product is going to be identity plus rescaled copies of of X, right? So identity plus 1 over n times a copy of the matrix X, and I take a product of n of these guys. So just to get some intuition for a second, the reason that I'm doing this rescaling is Zn in the limit has constant size, right? I'm sort of multiplying things that are of size, n copies of things that are of size 1 plus 1 over n. So Zn is an object of sort of constant size. And the Amelia Henriksen and Rachel Ward proof shows that this thing concentrates in the following way. So they prove some more stuff, but just thinking about an expectation, the expected spectral norm of Zn, the deviation of Zn from its expectation, scales like what? Something involving B, which is the almost sure bound that we have on the size of the matrices, and then some decay that's like polylog D and n over n under a square root. So the good news here is this 1 over root n behavior is exactly what you would hope for. Some logs, but who cares about logs among friends? And then some stuff that depends on B. So if you have B is equal to 1, for instance, this just looks like up to logarithmic factors 1 over root n, which is exactly the type of behavior that you would hope for and expect in this situation. So this was a really nice result. And I actually think that the result is so nice that I'm going to say some words about the proof, because I think that the proof gives some insight into the techniques that we have available when working with random matrices. And so the proof here is basically relies, yes.
Is it clear that I should not expect a D factor like I see for the matrix Bernstein case in front of the bound?
So I've hidden some things here. So the difference was in the matrix Bernstein case, I wrote down a tail bound, right? And then you would expect a multiplicative factor of D in front of the tail bound. But if I changed Bernstein to ask about what happens in expectation instead, then that D turns into a log D. Right, so the expected spectral norm is like a root log D factor bigger, whereas the probability bound is a factor D bigger. So here, since we're dealing with expectation bounds, the natural thing to expect is a root log D rather than a polynomial factor in D. So the proof idea here is just in the grand mathematical tradition of if you have a hammer, then look for nails. And so here we have one hammer, which is the matrix Bernstein inequality. And so Henriksen and Ward squeeze as much as they possibly can out of this hammer of the matrix Bernstein inequality. And they use this to analyze the product. So let me show how this works. So the starting place is, well, okay, I have a product of random matrices that are all perturbations of the identity. So first thing I might as well do is expand this thing, right, to understand how it looks asymptotically. So I can do an expansion of this. I start with the identity matrix, that's good. And then I have a sum of the first order terms, second order terms, and so on, all the way down the list. So let's try to apply matrix Bernstein to the thing we see here. So the first thing we notice is that this second term in the expansion, this is just a sum of bounded IID matrices, which is great because the matrix Bernstein inequality tells us that this thing is approximately the expectation of X. I have a sum of IID things. I can make precise the fact that this object concentrates around expectation of X. So far, so good. The first term works fine, and this is exactly what we hope it should be. Okay, what happens for the second term here? What happens for the second term here? Well, for the second term, I'm already having a problem, right? Because this second term is no longer a sum of IID terms, because there are some things in this sum that depend on each other, right? So for instance, the matrix X1 shows up in several different summands here. So this is no longer a sum of IID things. So Henriksen and Ward have the following very clever idea, which is, okay, this is not a sum of IID matrices for sure, but I can break it up cleverly in such a way that it is a sum of IID things. So what do I mean by this? So what we're going to do is, in place of this sum over all possible pairs I and j, we're going to partition this into sums so that each index appears exactly once. So to look at the first thing, right, I can take all products of the form x1, x2, x3, x4, and so on, and sum all of those. That's some subset of this total number of things that I need to sum over. And then I can do the same with other partitions, right? I can partition this into a bunch of things where each of these individual sums comprises only independent matrices. And then I apply matrix Bernstein to each of these. So matrix Bernstein for each of these says, okay, you've got a sum of independent matrices. They're IID, in fact. And so I know that they concentrate around their expectation, and their expected value, it's easy to see, is just expectation of X quantity squared over 2n, because each of these things is renormalized by 1 over n squared, and there are about n over 2 things per sum. Great, okay, and when I add these things up, what do I get? Well, I get precisely that this term is of order expectation of X quantity squared over 2. So we had to do a little bit of work in order to get this second order term, but luckily there was this very clever idea that if I broke this up, I could do it as a sum of truly independent sums of random variables, or each of these sums comprises independent random matrices. Okay, you might be optimistic about the fact that we did the second one, but things already seem much more complicated now that we're at the third one, right? So I was able to do this by hand somehow in the second one, but it's not clear that I'll be able to do it from the third one. So let's just get some intuition for what we did in the second one, actually. So I would claim that one way of thinking about what we did in the second one is we just noticed that the set of things we were summing over is just the edges in complete graph, right? So if I have a complete graph on 4 vertices and I label them 1, 2, 3, 4, then really what I did in breaking up this second sum is I decomposed this complete graph into some perfect matchings, right? So each of these things that I decompose it into is vertex disjoint, which means that every one of these is a sum of independent things. So really what we did in bounding this second sum is we just took the complete graph on n vertices and we broke it up into a bunch of perfect matchings. Well, in the third term, we have now a hypergraph, right? In the sense that I now have triples of indices from 1 through n. And it turns out if you open, you open your big book of combinatorics facts that Hungarians have proved, you know that there is actually a nice theorem about hypergraphs. So this is a theorem due to Baranier in the 70s that says that the complete hypergraph decomposes into one factors. What's a one factor? It's just a perfect matching in this sense. So I can take a complete hypergraph on like a 3 uniform hypergraph, or more generally a k uniform hypergraph, and decompose it in exactly this way into subsets that are all independent sums. And then if I apply matrix Bernstein independently to each of those things, then I get again that this object concentrates around its expectation. And I can keep doing this.
John,
so the idea is we're going to, yes.
So this decomposition, I mean, this is this is a decomposition for U statistics that shows up in, say, even Hovding's original 1963 paper.
Exactly.
So
yep.
you have the fact that you're using this complicated combinatorial arguments is so that you get the factor 6, or like what do you lose by using?
So we really need to be careful. Yeah, so good point. We need to be quite careful here about making sure that we don't lose anything in the constants, because as I'm about to say, we need these constants to be the right ones so that the sum of all of these things that we're concentrating around actually looks like the expectation that we care about, right? So I better see exactly, k factorial show up in the denominator for the k term in this expansion so that I actually get something near the expectation at the end of the day. So I don't know whether a sloppier argument will also get this, but I think the reason that Henriksen and Ward use this rather precise decomposition result is they really need to nail down the constant and what it concentrates around. So what we're going to do is, in order to apply matrix Bernstein, as I said, I see concentration for each of these things individually. And I'm just going to pay an enormous union bound to promise that all of these things are close. So I'm going to independently apply a high probability bound to each of these independent sums. And I'm going to guarantee that the resulting sum is close to the expectation that I want. And what have I lost here? So what is implicit in these approximate signs in all of these places? These approximate signs in all of these places? Well, matrix Bernstein tells me what errors that I should expect here. And what I should expect to pay is errors of order 1 over root n, which is good. And then I need to pay for the size of the matrices under consideration. So the first line, I'm summing IID matrices whose spectral norm is bounded by B. So I incur an error of B over root n. In the second line, I'm bounding products of the xi's. A priori, their spectral norm could be of order B squared. So I'm bounding sums of independent random matrices with a spectral norm bound of B squared, and so on down the line. So because I have, because everything's happening on the exponential scale here, ultimately at the end of the day, I pay exponentially for this B, because the error gets bigger and bigger as I bound these things going down the line. So we get concentration around the expectation that we want, and our error scales like B to the 1 over root n, exponential of B to the times 1 over root n, which is exactly, as I said, what you see showing up in the Henriksen-Ward bound. So again, the whole idea here is just apply matrix Bernstein over and over again and bound everything together, and that's how you get the following bound. I should note that Nikhil Srivastava and his group at Berkeley improved this proof a little bit recently. They removed the log factor in n and simplified the proof, but the rest of the bound looks exactly unchanged. So this is the state of the art before our work, and this was the starting question for us, whether this is in fact the tight results that we want. And I guess the thing that would draw one's eye in this theorem is the following. Do we really need to pay exponentially in B here? Now you might say, first of all, that like, yes, we should pay exponentially in B, because maybe this object Zn is about of size e to the b, right? I mean, if each of the xi's are indeed of size b in spectral norm, then Zn in spectral norm, yeah, maybe looks something like e to the b. So this sort of seems like a natural scaling when you look at it the first time. Maybe this is unavoidable just because that's the size of the object on the left-hand side. But a moment's thought will convince you that this is not as sharp as it could be. Because if you go into the scalar case and just think about what would happen for scalar random variables, the optimal bound looks almost exactly the same, except instead of paying exponentially for b, which is the size of the almost sure bound on these random variables, you pay exponentially for the typical size of these random variables, namely the expectation of x. So in the argument that I gave a second ago, indeed, if x to the b, if x is always of size b, basically, then maybe indeed the typical size of Zn is e to the b. But nothing in the Henriksen-Ward argument is able to adapt to the fact that the typical size of these random variables might be much, much smaller. So the question here is, in the scalar case, we have a bound that looks very similar, but is it possible for us to recapture in the matrix case that I should pay for the typical size of the matrices, not the worst case size? And so
could you say a word about
now?
Could you say a word about how
Yeah.
you get the scalar bound?
Sure. The scalar bound is is just coming from the fact that, let me see if I can write here. Let me just take the logarithm of everything we see. So the reason that the scalar argument is easy is because I can take logs everywhere, right? So it turns out that if these conditions actually hold, then let me just look at log of Zn instead, which is a sum of IID random variables. And if I believe that the xi's are bounded and n is large, then this looks a whole lot just like the sum of xi over n. Right, so everything I know about bounding sums of IID random variables, after I take a logarithm in these precise asymptotics, it actually is no more complicated than like Houghton or Bernstein inequality, just applied on the logarithm. And then at the end of the day, you get something that looks like, so let me see if I can erase this. So what one gets at the end of the day is that log of Zn is approximately expectation of x plus a term that's of order like root b over n. And then when I take the exponential of this thing, this term turns into this term, right? And because b over root n is small, that x of b over root n just looks like 1 plus b over root n. So I get something that looks like exactly the b over root n that comes from here. So it's just applying it to taking the logarithm and applying sums. And of course, I should point out that this proof that I just gave is like extremely far from true for the matrix case, right? Matrix logarithm doesn't even make sense unless I have PSD matrices, and then when things don't commute, I don't have this ability to pull apart the sum. So none of what I just said makes sense in the matrix case, but that's why it's so easy to prove for scalar random variables. So what are we able to show? So what we show is a bound that looks exactly like the bound on the previous page, except that we've made the crucial change that instead of paying exponentially for b, we pay exponentially for the size of the average of the xi's, the expectation of the xi's. So the bound looks exactly the same, except that I have e to the mu upstairs rather than e to the b in my tail bound. And I'll say that, you know, we actually develop sort of more general tools for many different types of products of this kind. But in this particular case, I'm just trying to compare with the Henriksen-Ward results to see where the improvement comes in. So we get exactly this thing. And actually, sort of like the matrix-Bernstein case that I discussed earlier, what happens is that we end up getting a tail bound that looks exactly the same as the scalar tail bound up to constants, except for this d out front, which was exactly what happened in the matrix-Bernstein case. I had a tail bound with a particular exponent, and that tail bound showed up exactly in the matrix case, just with d out front. And the same thing happens here. So really this captures, at least at that level, the exact behavior we would want for the scalar case just in the matrix setting. And to convince you that this improvement is in fact meaningful, just to parse these for a moment, notice that this yields an exponential improvement in several cases of interest. For instance, if my random matrices are centered, then this improvement is huge, right? I go from something that depends exponentially on B to linearly on B. So in the centered case, this like destroys an exponential factor in their bounds. And in a slightly less trivial case, if I have xi's that are, say, isotropic coming from the sphere, we often should expect to see a factor of d difference between the worst case bound and the expected bound. So for instance, if I'm uniform on a sphere of radius root d, then my worst case bound, the size of this matrix in spectral norm is actually d, because the length of xi is root d. But typically, when I take the average, I just get the identity, which in spectral norm has size 1. So even if I'm dealing with PSD matrices, it can be the case that the worst case bound is like a factor of d bigger than the expected bound. And there we see that the exponential dependence on D that's in the Henriksen-Ward bound disappears when you apply ours. So this is all to say that, I think that one nice thing about these results is that there are cases where the Henriksen-Ward bound the bound is too large to be meaningful. You need N to be exponentially large in D to get any meaningful concentration. Whereas here we can afford N much, much smaller than that and still have a non-trivial bound. So let me now turn to saying some words about the proof. It turns out that the proof of this improved bound is much, much conceptually simpler than the bound that Henriksen and Ward do. We don't use matrix Bernstein. We just try to apply first principles ideas to this product and see whether we can get anything just by examining it in a very general framework. And this general framework we're going to explore is just to say, rather than thinking about these as matrices, let's just think about them as random elements in a Banach space. So the space of D by D matrices equipped with the Schatten P norm, which is defined in this way. The P norm of X is just equal to the trace of the absolute value of X to the P. And by absolute value of X, I mean the matrix absolute value. So it's X transpose X to the 1/2. So when X is PSD, this is just trace of X to the P, or more generally, I have to just multiply by X transpose. So this is the Schatten P norm, and we're just going to analyze directly random elements in this space. And the intuition will be that as long as this norm is nice enough, sufficiently Euclidean, we will get good concentration results for free, essentially. So this uses ideas that are well known in geometry of Banach spaces. So Asaf Naor has a nice paper where he sketches ideas like this in more detail for Banach valued random variables. But the high level intuition just is if this norm looks smooth, looks familiarly like the Euclidean norm, then I get something that automatically gives me good concentration. So to see how this works in practice, let's just see if we can figure out how to prove the following simpler claim. So what I'm going to try to prove for you together today is like, if I have a bunch of centered random matrices with an almost sure bound on their size, what we're going to try to prove together is that the expected norm of this random product is small. It's 1 plus something that looks like B over root N. So again, I want to contrast this with the bound that you would get if you were just thinking that these X's were as large as they can possibly be. The worst case bound, the worst case size of this object is exponential in B. Whereas the bound that we would hope to prove, which is a simpler version of the theorem I presented several slides ago, just says that actually typically the size of this product is like 1 plus a factor that decays like B over root N. So let's step through an idea of how to prove this. So what should we do first? So here's a first attempt for how to prove this. Oh, there's a chat. Is this, oh, that's from Philippe to everyone? Okay. So the first attempt for how to prove this might be like, okay, let's do something that's familiar to people who have worked on matrix Bernstein or other random matrix concentration inequalities. Let's just, instead of bounding the spectral norm, let's apply Jensen and the monotonicity of the Schatten norms to bound the squared Frobenius norm instead. Right? The operator norm is a bit of a pain, but let me work with the Frobenius norm, and this is something that I feel I can handle. And because the Frobenius norm is always bigger than the spectral norm, I can just bound this thing and get a good upper bound for the quantity I want. Okay, so I have the spectral norm, I have the Frobenius norm of this thing. Let me develop this a little bit. And the chat is, oh, okay, so there's a question about the, so great. So there is a, let me back up here to, so the question was, does this requirement that N is large enough so that N is larger than B squared log D, is this actually necessary? And is this part of the general bound too? So the answer is sort of yes. I would recommend that you look at the paper for this. The answer is yes, and you can actually see that this is true even in the scalar case. Basically, when N is not big enough, when N is not bigger than B, or N is not bigger than B squared yet, then this thing is actually exponentially large, typically exponentially large. So before there's an elbow effect in what you expect, and this is tight, it's true even for the scalar case, in what you expect the size of this thing to be. This thing is large, or can be large early on. There's no good reason for it not to be large. But once n is competitive with b squared, you concentrate near 1. So there's something going on, and this is a consequence of the fact that the tails of this random variable they can be quite bad, actually, because I'm taking the exponent of a random variable. Like, this thing has very poor decay. It looks like a log normal random variable away from the origin. So you do need some requirement that n is large enough to write down such a thing. Okay, so let's go back to this. Let's go back to this expansion. I said let's pass to the Frobenius norm. Then I can just use the definition of xn. And let me write here. So zn is just exactly what you think it is, or zn minus 1. Zn minus 1 is just the same product, but with the last guy lopped off. Right, so I can peel off the first factor here, and I'm just using the explicit expression for what these products are. Now what? Well, okay, so now we actually have something non-trivial we can do, which uses the fact that because the Frobenius norm arises from an inner product, and because x is conditionally mean 0, given zn minus 1, I can do a bias variance decomposition here, right? So I can get something that's the expectation of this object, which is just the first term, and then I get something that looks, so this is the expectation squared, and this is the squared expectation. This is just a bias variance decomposition of this object up here. And this was, of course, only possible because I was able to use the fact that the Frobenius norm arises from an inner product. This is a Euclidean norm, so I can just pull this thing out by passing to the inner product and recombining the squares. Okay, so what does this give us? What can we do now? Well, the obvious thing to do now is just to say, okay, the first term is whatever it is, and I know the second term is small because xn is of size at most b. So by using the fact that I can pull out the product of the xn and the zn minus 1, this thing is of size at most 1 plus b squared over n squared times expectation of the product at time n minus 1. So now we have a recursive bound. The key thing is I can keep peeling off factors of xn, and each time I do, I get a factor of 1 plus b squared over n squared. And when I do this n times, okay, what happens? Well, at the end, I'm left with the identity matrix plus a bunch of these factors of 1 plus b squared over n squared. And importantly, this 1 plus b squared over n squared to the nth power still gives me something small, in the sense that if n is of order b squared or bigger, then this is something that goes to 0 as n goes to infinity. Or it goes to 1. So b squared over n goes to 0. So this thing gets smaller as n goes to infinity. So compare this again with the trivial bound, which said that zn could be of size e to the b, could be of size e to the b, which in no sense went to 0 as n went to infinity. So this is already a good thing. Of course, this factor of d is bad, right? We don't want to pay polynomially for d, and this thing is not even near 1, right? It's something of order d instead. So just to say this again, because this is the key point for the proof that we're going to use, because the Frobenius norm arises from an inner product, I can apply this bias variance decomposition and then bound brutally the xn by its almost sure bound b in order to get a recursive bound of this form. And if I peel off n factors of these, I get something that scales like e to the b squared over n times the 2 norm of the identity matrix. Of course, as we saw on the previous slide, the problem is that I cannot do this using the 2 norm because the bound that I get is simply too loose. So I'm caught in a double bind. The bound that I get from the 2 norm is too loose, but of course the 2 norm is the only Schatten p norm that arises from an inner product. So I'm sort of stuck here because I would like to do it in a different norm, but I can't because it doesn't come from an inner product in general. And the insight is that there's this concept called uniform smoothness of Banach space norms, and the Schatten norms in particular, that allows us to mimic this argument even in other norms. So to motivate the definition of uniform smoothness, let me just remind you what it means when I say that a convex function is smooth. I say that there's an upper bound of this quadratic type around any point x if the convex function x is smooth. And one way to say this in maybe what seems like a slightly obscure way is this implies that Jensen's inequality is tight up to a factor that's like L/2 times the size of the perturbation squared, right? If I take this inequality on the first line and apply it to x plus tau and x minus tau, it just shows me that this is like f of x plus something that depends quadratically on the size of the perturbation. So motivated by this definition, we can say that a general norm in a general Banach space is too uniform smooth if the exact same inequality holds with some constant k. So I ask for x plus tau and x minus tau, the square of these things, to be like norm of x squared plus something that depends quadratically on tau, the size of the perturbation. So notice, for instance, that for the Euclidean norm, this just holds automatically with k equals 1 here, right? So if I have the Euclidean norm, then it's always the case that x plus tau squared and x minus tau squared, the cross terms disappear, and I'm just left with tau squared plus tau squared over 2. So I get k is exactly equal to 1. And the point is that if I have a true uniform smooth thing, a true uniform smooth norm, then I can still do a bias variance decomposition at the price of a factor of k. So this would be, again, inequality with k equals 1 for the Euclidean norm. But if I have uniform smoothness, then I get an inequality with a little bit of extra in front of the b. And just to tell you why this should be true, let's pretend for a second that instead of being mean 0 conditioned on a, let's pretend actually that b and minus b have the same law conditioned on a, so that actually this is a symmetric random variable. Well, then the expectation of a plus b squared, I can think of that as the average of a plus b squared and a minus b squared, because b and minus b have the same law. But then if I just apply the smoothness inequality, I get exactly this inequality that I've claimed on the first line. I get expectation of a squared plus k expectation of b squared. If b and minus b do not have exactly the same law, if they're just mean 0, I can use symmetrization. If you do symmetrization naively, you get not exactly the factor k here, but you get a different constant that's like a constant bigger than k. It takes a little bit of cleverness to actually get the sharp constant k. But it turns out that whatever constant was in uniform smoothness, you get exactly this same constant in this bias variance upper bound. And how will we use this? Well, just like Oliveira and Trop used a single fact, deep fact about matrices, and then everything followed from there, we will use a single deep fact about matrices, which is this famous bound of Ball, Carlin, and Lieb, which tells us that the Schatten P norm is too uniform smooth, with a particular constant k that depends on p. So the whole story here is that we know that this particular property of Banach spaces is possessed by the Schatten P norms. And so what we can do is mimic precisely the proof that we had in the case of the Frobenius norm, which happens with p equals 2, by an analogous proof in the case of the Schatten P norm at the price of an inequality sign, which we don't care about, and an extra factor of p in the bounds. Otherwise, the proof goes through entirely unchanged. And what happens if I recurse this bound? Well, the first term, again, looks like what I expect from the previous example. I have n iterates of this 1 plus p times b squared over n squared, and then I have something that depends on the p norm of the identity matrix. And so in a balancing act that will be familiar to anyone who has worked with these matrix inequalities, the first term in this bound gets better as p gets, the first term in this gets better for small p and worse for large p, but the second term gets better as p becomes large. So if you just balance these two things, then you get exactly the claimed bound. So to answer, again, the question from earlier, the actual bound you get is this thing. It's still of exponential size, but when n is large enough, this exponential of b just looks like 1 plus something that scales with b over root n.
What's the order of
so this
p
is,
you end up getting?
what's the order of what?
Of p?
Oh, you have to choose, it's whatever balances these things. Let me see if I can do it online. So p is equal to like root n log d over b or something like that. P is large. Yeah, p is very large, but it's, it's literally just balance these things, and it's like I said, something like root n log d over b squared. Okay. All of the proofs in our paper for everything, so including inverses of products of random matrices, adapted sequences, tail bounds, everything comes down to this basic idea of using uniform smoothness. And as I said, the results are not only an improvement over the Henriksen-Ward results, but I think are significantly conceptually cleaner. So I just want to end, since I'm running out of time, with some open questions. This is far from the last word on products of random matrices. This is really just the first step to understand properly how these products behave. I think that the clearest open question here is the following. When xi's are independent but not IID, so they may have different expectations, if you go to the theorem in our paper, the main bound scales with the e to the average norm of the expectations. When really, one thing you might hope is that it would scale with the norm of e to the average expectation. So the first thing is always bigger than the second thing, but you might wonder whether it's possible in general to replace all of the bounds we have here with something that looks like this. And one interesting fact is actually we know that's not true. We have some examples where this is the tight behavior and the second bound does not hold, but some examples where this is loose and actually something of the second form is true. So I think the meta question here that we don't yet have a good handle on is, what is the right quantity that should show up in these bounds? It's not this, but it's not this either. So there's still a question about, what the truly right scaling for this tail bound ought to be. One instantiation of this question, something that we don't understand at all, is that all of the bounds we've had are insensitive to the orderings of these random matrices. So in the sense that if these random matrices are independent but not IID, so different ones have different laws, we get exactly the same bound no matter what order these random matrices come in. But we can show by example, essentially, that the ordering matters a lot. So there are some permutations of random matrices which concentrate much, much better than other permutations. We don't have any bounds that are able to pick this up. So again, I think that this is a situation where we don't know much yet about what the true situation should be. The question, I have a question from the Q&A, could we easily extend the proof to IID Gaussian xi's? So if the xi's are entry-wise Gaussian, say, or something like that? Yeah, so I guess the thrust of the question is that, of course, if they're Gaussian, we don't have an almost sure bound on the size of the matrices. Instead, we have some sort of moment bounds. And the answer is totally yes. If you look in the paper, we have examples where we have much weaker conditions. So if I have, in general, unbounded random matrices, but whose moments can be well controlled, then the same story holds. And that's all I wanted to say. So we have this this new set of tools that I think give us good control over products of random matrices, and maybe are the first step in what I hope is a much more sophisticated understanding of compositions of random operators. And if you have any questions, the paper's on archive, or I'm happy to answer anything now. Thanks a lot.
Thank you very much, John. So I'm guessing you're getting virtual applause. So how about we try the following. If you have a question, just let me know in the Q&A, and I will try to click this allow to talk. Just be mindful that the talk is being recorded, and we plan to include questions if you have some. So I need to let you know about this. So are there any questions? So while people are thinking about it, I wanted to actually ask maybe a more general question. So when you looked, you described this Henriksen-Ward approach. which is really very much a U statistics approach. I was wondering, so here in your results, you use a very specific form of the product of random matrices where you peel them one at a time. I was wondering if I actually want to understand generally U statistics of random matrices. Are there any general results for this, or is the Henriksen-Ward the only result that we know about this?
Not to my knowledge. I mean, again, there's some, if you squint, some of the results in the literature end up looking like asymptotic questions about U statistics of matrices. I mean, you have, again, this law of large numbers type thing, so you get consistency of various estimators based on U statistics of matrices. But apart from Henriksen and Ward, I'm not aware of non-asymptotic concentration results for general U statistics of random matrices.
I see, thanks. Any other questions? So again, if you have a question, please enter it in the Q&A, and I'll give you the ability to ask it yourself. So I actually have a second question. So uniformly smooth norms, is that related to type?
Yeah, so it's related to martingale type. So this is one way of seeing this. So let me go back to, so this is a perceptive remark. So if I go back to this proposition, like what does this look like, right? So to say that expectation of B conditional on A is equal to 0, I mean, this is just saying that A followed by B is a martingale difference sequence, right? So this is allowing me to peel off factors from a martingale difference sequence. And if you iterate this, you get exactly what looks like a martingale type inequality. So this is, yeah, this is totally related to that.
Okay. All right, so thank you very much, John. It doesn't seem like we have any other questions, so it's probably time to end this meeting. So I would like, there is a question by Kwang Jun. So Kwang Jun, I'm going to give you the ability to speak if I find you in the list of allowed to talk. All right, you can unmute your, so you're unmute, sorry.
Thank you. So actually I'll type my question on the QA section. So my question is, throughout the talk, I was under the impression that like free probability can answer the regime where n is small, but d is large. And your work kind of covers the case when n is large and d is small. And my just like question out of curiosity is, would it be hard to analyze the regime where n and d are both small?
So I think that you have to ask what type of answers you hope to get in that regime, right? Like if we go back to the very beginning, questions about concentration of measure, you know, we're looking here for something concentrating around its expectation. And so if I even think of sums of random variables, you can say like, what can we say about the sum of two random variables? So certainly you can say some things about that sum, especially if you know things about the individual summands. But the thing that you won't get is stuff that looks like a sum of two random variables concentrates well around its expectation. I mean, no better than the individual ones will. So you can try to analyze, like this procedure gives you something to analyze products of a small number of random matrices, but I guess the question is what type of answers one hopes to obtain for those things. And again, there are answers in I presented theorems today that require n to be large enough, but there are statements in our paper that hold for all choices of n and all choices of d. It's just the case that normally when n is super small, any sort of concentration result is uninteresting.
So thank you very much.
Thank you, Quentin, for your question. Any other questions? Yeah, Paxton has a question, so I'm going to give you so if you have a question, just say I have a question, and I'll allow you to ask it online. So let me allow you to speak, Paxton. Where are you?
Okay.
Oh, well.
Thanks, John, for the talk. These are some nice results. I was just wondering of what examples you're aware of where these matrix products appear. I saw an exposition of this Heinrichsen paper before, and they talked about streaming PCA, but just wondering if there were others that you were aware of.
Yeah, so the easiest example, so streaming PCA, which also goes under the name Ojha's algorithm, is one example of basically doing its stochastic gradient descent on a quadratic, essentially, is what's happening in streaming PCA. And so more generally, products of random matrices arise whenever you are doing stochastic gradient descent on some object that is locally well approximated by quadratics. So, you know, this is not in our paper yet, but you can answer similar questions about SGD on smooth and strongly convex functions, because those just look a lot like quadratics locally. So composing these random operators looks a lot like multiplying random matrices. As I said, the other example that people have used this for, so there are a couple of recent papers. One of the names associated with this is Boris Hannon, and I think there are some others who are, so I said, looking at deep neural nets. And what they ask is, okay, I have a deep neural net randomly initialized with many layers, and I want to understand something about the Hessian of the, you know, if I take the Hessian of this function with respect to the parameters, what it looks like. And so when I do this layer by layer, I get a product of matrices because I'm composing, and each of these matrices looks like a random matrix with some structure because I've assumed that I'm randomly initializing the weights. So it turns out that you can prove some things about the dynamics of neural networks that seem to match what's in experiments by just pretending that your Hessian is always of this form, always looks like a product of random matrices. And so there again, in the way that they've been able to analyze it in the past is just in the asymptotic regime. So the asymptotic regime with, say, infinitely deep nets, or a particular width and depth scaling asymptotically together, our results offer a non-asymptotic take on this same picture. You know, if I actually want to understand with high probability near initialization what the landscape of a neural net optimization problem looks like, then I can look at this random composition and say that it looks like its expectation with some deviation that's small, as long as the net is deep enough.
Okay, great. Yeah, that's really nice. Thanks, John.
All right, so I'm not sure there's any further questions, but we're a bit over time, so I'm gonna close this first virtual meeting. Thank you everyone for participating. Let me remind you that next week, Arias Castro is speaking in the same seminar. Let's thank all John virtually, and hope to see you all next week. Thank you.